this video, we'll discuss about radical inequalities and graphing of irrational functions. So let's start with the inequality. So what is a radical inequality? Definition is simple. A radical inequality is an inequality that contains a variable within a radical. So there are two keywords here. An inequality, so it has to contain any inequality symbols like less than, equals to, or greater than. And then in the radicand, you have variables. So the variable within a radical. So this is a radical inequality. I give you two examples. I hope it's clear. So let's go to the next one, the steps. So the steps of solving radical inequality will be, first, you need to find the root index of your radicals. So if you have a complete statement of inequality and there is a radical or there are more than one radicals, check whether you have radicals with the root index even numbers. For example, 2, 4, 6, and so on. If you have this, you have to identify the domain for which the radicand is non-negative. Why? Because for any radicals with the root index even numbers, you cannot have the radicand negative, which it will make imaginary numbers. So since the domain that we are dealing with is real numbers, the domain will be limited if you have radicals with even numbers as its root index. I will get to that later on the examples. So the second one is solve the inequality algebraically. And for this one, of course, you need to recall back the steps when you solve equations because it will be the same. When you solve the inequality, it will be the same with when you solve equations. You isolate the radical and then you square or cube both sides, and then if you still have radicals, you repeat the steps until you get rid of all the radicals and then you solve it. Just recall back all the steps on the solving equations. And the last one, the safest way is to test the values. Okay, check your solutions whether it is correct or not. So let's go to the examples to make it clearer. And this one, I'll give you three examples, and this is the first. So as you can see here, this is a radical inequality since it has inequality sign, and the radicand contains variables. So yeah, this is radical inequality, and we can see that the index is 2, so it is even number. It means we need to specify the domain. Since the domain is limited, the radicand must be non-negative, so 3x plus 2 cannot be negative. It has to be greater than or equals to 0. So when we try to state it in other form, so we know that all values of x that is greater than negative 2/3 will be your domain. Since if it is less than negative 2/3, it will give imaginary numbers. So let's solve the inequality. So let me just write down again the problems. So the first step, when we recall back equations, we have to isolate radicals, right? So let's just add by 1 both sides, and then we can have square root of 3x plus 2 is greater than equals to 5. And then after we isolate radicals, let's get rid of radicals by square both sides. When we square both sides, in the end we have 3x plus 2 is greater or equals to 25. And then let me just subtract both sides by 2. We isolate the x, of course. Let me just write down here 3x is greater or equals to 23, and then the last step is divide both sides by 3. When we divide both sides by 3, we have the last statement that all solutions that satisfy your inequality will be all x that is greater and equals to 23 over 3. So let me put in on the number line. It begins with a closed circle, of course, because there is an equal sign there. It is 7 to third. 23 over 3 is 7 to third. So because it's greater than, it must be all values that is greater than this one. So it is on the right side. So let me compare with the domain. Of course, the domain, it is negative 2/3. It is around here. So all values that your solution is acceptable because it is inside the domain. So there's no issue here. So let me do the testing as the final steps. Let me test whether these solutions are true. Let me pick any numbers from these sections. For example, I pick 100. Okay, 100 is from the solutions that you have found. So if I put into the original inequality, I have 300 plus 2 minus 1. Well, of course, square root of 302 is, well, you can have the sense that it is true. So yeah, this solution is a true one. So let's go to the example 2. When we have different situation here that, yeah, you can see that it has the domain, okay, because the index is 2. So the radicand, which is 20x plus 4, cannot be non-negative. It cannot be negative, so it has to be greater and equals to 0. So let me just try to change the statement so we can have x is greater and equals to negative 1/5. Okay, so all values that is greater and equals to negative 1/5 will be acceptable since it will give you real numbers. But then this is not the solution, so let's just solve it. So since the radicals is negative, try to avoid that. So let me just please first copy the problems. And I want to move, let's just say move to the right, since I want to get rid of the negative before the radicals. So I add both sides by square root of 20x plus 4, both sides. So I will go to this area so we can have more space here. So it becomes 5 is greater and equals to square root of 20x plus 4 minus 3. You can see there that the coefficient of the square root is positive, so it's good. So let's just add both sides by 3 because we need to isolate the radical. So it is 8 is greater and equals to square root of 20x plus 4. And because we have isolated the radicals, let's just square both sides to get rid of the radical sign. So we have 64 is greater and equals to 20x plus 4. So now the last state is we need to isolate the x. So we subtract both sides by 4, and then we have 60 is greater and equals to 20x. And the last statement will be when we divide both sides by 20, I change the position, so its x is less than equals to 3. So the solution is all x that is less than equals to 3. But the domain specified that the x must be greater and equals to negative 1/5. So let me just put on the number line first the solution. So the solution will be all values of x that is, oops, okay, sorry with the line here. It's supposed to be used the ruler. So yeah, this is the all solutions. But of course, we only accept all values of x that is greater and equals to negative 1/5 because it will give you real numbers. Aside of that, it will give you imaginary. So let's combine both domain and the solution, and in the end, we have that all the solutions that is acceptable from based on the domain and the solution itself is all values of x between negative 1/5 and 3 inclusively. So yeah, the last step is let's test whether this area is true. So let's just pick any numbers from this area. For example, I will pick if x equals 1. Let me pick 1. So I put 1 into the inequality. I have 5 minus square root of 24. Is it greater and equals to negative 3? Because square root of 24 is less than 5, of course, it is greater than equals to negative 3. So this is true, and it's checked. So that's how you solve radical inequality. But for the sake of variety, let me just give you one more example. Let's go to the next example, example 3. Now this one, we have cube root. Cannot square root, the root index is odd number. So if the the root index is not an even number, it means that the radicand can be negative, can be positive, and it still give you real numbers. So the domain is all real numbers for your x. It's acceptable. You can use any real numbers since the radicand can be freely negative or positive. So let's just directly go to the solving the inequality. So first let me copy the problem first, and then the first step for solving is isolating the radicals, right? So let's just subtract both sides by x and add both sides by 2, and in the end we have cube root of x plus 2 will be greater and equals to x, no, it's 1. Okay, so after that, after we have isolated, let us just cube both sides, and then it will be x plus 2 greater and equals to 1. So let's just isolate the x by subtract both sides by 2, I'm sorry. So it's x greater and equals to negative 1. So the solution will be all values of x that is greater and equals to negative 1. And the domain itself will be all real numbers. So the last step is testing whether this is true or not. Let's just pick any numbers from your solutions. So if I just pick like 6, okay, 6 is one of the numbers on your solution. So it will be cube root of 8 plus 6 minus 2 greater equals to 6 minus 1. So cube root of 8 is 2. So in the end, it will be 6. It's greater and equals to 5. It's checked. It's true. Therefore, I can be sure that this is my solution, the number line. Remember, for all inequality, the solution must be in a number line form in this class. So now, we have done with the inequality. Now we are going to the graphing. So for graphing, it's simple. Okay, let me just give you directly examples. This is the first function that we need to graph, because for this one we are dealing with irrational algebraic function, so it will be a function of x. I replace y by fx, so it can be y equals 3 plus square root of x plus 2, or we can use fx. It's the same. So how do we graph this? The safest way is by using the tables of pair, right? The table of pairs. So let's just use any numbers of x and then put it into the function and then find the value of your y. But of course, we can see that there is a specified domain for your x. Why? Because we know that this is a square root, so your radicand cannot be negative, right? So therefore, for any positive or 0, it will still give you a real values for your y. So let's first specify our domain. The radicand must be greater and equals to 0. Therefore, the domain is all real numbers that is greater and equals to -2 will be the domain. So you can put any real numbers except all numbers that is less than -2. So let me just show you the table of pairs. The table of pairs shows you that when I begin with -3, okay, it gives me imaginary numbers. Yes, of course, because -3 is outside the domain. And if you want to experiment using other values of x that is outside the domain, it will consistently give you imaginary numbers, right? So let's begin with -2, so I can have the first real values for your y, which is 3. And then when I go to the bigger number, which is -1, I still have real values and so on. In the end, if I'm just giving you any numbers that is greater than -2, I can have real values of my y. And you can see it's increasing, right? Increasing until positive infinite. So let us just plot it, okay, using the graphing software. We can see that actually it begins here. This is the starting point at -2, 3, this one. So this is really, there's no arrowhead, don't forget, because it's really stuck there. And then when I plot it, the pairs, it shows you a curve, and then it's like a half of a parabola, okay, but it will be consistently increasing until positive infinite. So this is the graph, and the domain is this. So actually I can be certain that I can find the range, which is all values of y that is greater and equals to 3, right? Because your graph shows you that it only contains the value of y begins with 3, goes up. So all values of y that is greater and equals to 3 will be your range. So don't forget, in this graphing, we have to recall back about the domain and range, because it might, it can be assessed also on your test. So let me go to the next example, the last one. For example, this is my new equation, new function. You can see there is a difference. Look at this. And you can experiment. Look at it. This is addition, and then this one is addition. For the new one, it is like begins with -3, subtraction, and this is another subtraction, and look at the order. So you can try to experiment with other kind of radical function and try to plot it and find how the graph behaves. So for this one, let us specify the domain first, because we need to know our limitations of what values of x that we are allowed to use, right? So we can see this is a square root. It means we need to be certain that the radicand must be non-negative. It must be 0 or positive numbers. So the domain will be 2 minus x is greater and equals to 0. So when I try to transform it into other form, so it will be all values of x that is less than equals to 2. It means your graph may only show all values of x that is less than equals to 2. If I use x values the values of x that is greater than 2, it will give you imaginary numbers, right? It will make the radical negative. That's why when I put 3 into this function, I will have imaginary numbers. But when I start with 2, okay, and then I go to the lesser numbers, I'm sorry, it still gives you real numbers for your y, because yeah, it is the domain. So look at it, -3. It begins with -3 and then it's decreasing. So this one is decreasing. So when you plot it, actually this is your graph. So it ends here. So if we are or it starts here, it depends on your perspective. So it is stopped. At this point it stops. There is no arrowhead. This is coordinate 2, -3. And then you don't have any curve, you don't have any graph when the value of x is greater than 2, right? But you can have your graph when the values of x is less than 2. And the value of y begins with -3 and then it goes lesser and lesser. So the range will be all values of y that is less than equals to -3, because it continuously go to the infinite negative. Okay, or negative infinite, sorry. So yeah, we have many variations. Try to improvise, try to check with your graphing, try to find out there is like a specific pattern regarding the composition of your function to your graph. But in the end, the safest way is using table of pairs. But don't forget, you need to specify first the domains, since if you not specify it, you will have the value of y imaginary numbers. So we need to know the borders, right? We need to know what are the values of x that we can use to give you real numbers for your y. So yeah, that's it for your graphing. It's simple. So this video explains you about both inequalities and graphing, and that is the end of chapter 8 material, irrational algebraic function. Hopefully this video helps you to understand more about this. Thank you for listening.